This lecture we'll be discussing Le Chatelier's principle, and in Le Chatelier's principle it's all about when a system's at equilibrium and you perturb it or change it in some way, how does that system respond? And the flowchart on the title slide I think gives a good overview of that, a good summary. Okay. So if we start here when our system is at equilibrium, and in this case it's just a very simple A goes to B. So right here our system's at equilibrium. Well, what happens if we stress it? Okay, so where A is not in equilibrium with B anymore, right? Then you have this kind of a flow chart here of things to try. Okay, then you compare Q to K. Okay. Do they equal, right? And if they do equal, then, right, that means you're back at equilibrium. Okay. If they're not equal, then you can ask yourself, is Q less than K? Yes. If so, the reaction would go forward. Is Q less than K? No. Q is bigger than K. The reaction would go in reverse. And that happens until Q equals K, in which point you're back to equilibrium. So I think that's a good, really overview of equilibrium in general and Le Chatelier's principle. Right, so last time we learned how to solve equilibrium problems using reaction tables or ICE tables, and we'll be doing a little bit of that, more of that today. This is from section 17.6. In the book, Le Chatelier's principle, we'll be talking about the basics of this, and then we will also jump back to chapter 20 and talk about using the equilibrium constant K in our calculations for delta G. Right? And so this is why just the order we do things in this class, we didn't cover section 4 in chapter 20 before because we hadn't yet discussed equilibrium and the equilibrium constant. So this will make much more sense now that we've covered chapter 17. Right. So Le Chatelier's principle. Okay. And basically it's stated as when a chemical system at equilibrium is disturbed, it retains equilibrium by undergoing a net reaction that reduces the effect of the disturbance. Okay. So if a system is disturbed by conditions that force it to go out of equilibrium, and the system will respond to this disturbance by a shift in the equilibrium position. A shift to the left is a net reaction from product to reactant, and vice versa. A shift to the right would be a net reaction from reactant to product. Right. So if you think about in terms of just a simple reaction, A goes to B, if the concentration of A increases, the system reacts to consume some of it. So if you add A in, it will try to consume that and force it to B. So if A is a reactant and you add it, the equilibrium position shifts to the right. Right. If it's a product that's added, the equilibrium position would shift to the left, the opposite. Right. The other way you can change concentration is if you decrease a concentration. So let's say the concentration of B decreases, the system's going to act to consume some of it. So if a reactant is removed, the equilibrium position is going to shift to the left towards that side of the equation. If a product is removed, the equilibrium position is going to shift to the right. Okay, so if you add a compound to this system at equilibrium, that will push the arrow in the opposite direction, the other side, and vice versa. If you consume or remove some of the compound, it's going to shift the arrow to the same side that compound's on. only substances that appear in the expression for the reaction quotient, Q, can have an effect. So remember, things like solids and pure liquids don't show up in that equation for Q, so they're not going to affect the equilibrium position in terms of Le Chatelier's principle. A change in concentration in these any reactant does not have an effect on the value of K. And remember, we calculate Q and K the same way. They use the same exact formula, right? But it's important to remember that K is a specific, you can think of K as a specific situation of Q that happens at equilibrium. And K doesn't change for a system, assuming you're at the same pressure and temperature. Okay. So if you change a concentration, that's going to affect Q, but that will not affect K. So if we look at this reaction, we have PCl3 plus Cl2 in equilibrium with PCl5. If you increase any of the reactants or decrease a product, all of those effects would cause a shift in this equilibrium to the right. Okay, if we perturb it in that way, it's going to respond with pushing the reaction towards the right here. And vice versa, the opposite. If we decrease either of these two or increase this one, the shift in equilibrium or the shift in the reaction will go to the left. How would we handle this in terms of a reaction table? So we can think about the last time we discussed reaction tables. Okay, what if we had these concentrations to start with in our chemical reaction, and these are the equilibrium conditions. Well, you could use those to calculate the equilibrium constant, right? And then our problem might say, okay, there was a disturbance. We added more of the Cl2. So then you take that into account. So now we're adding a new row to this column where we have a disturbance. Okay, so in this case we're adding 0.075 molar of concentration of Cl2. Okay, so then we would add our original equilibrium plus whatever the disturbance was. We'd add that up, and that's now our new initial concentrations, the I from the ICE table from last time. Okay. Now we can do, changes. So we know that now it's not at equilibrium anymore, so there will be changes. We know that we've added a reactant here, so that it's going to push the reaction to the right. So these will go down in concentration. So the change will be negative X. The product, PCl5, sorry, that's a typo. That should be a 5 there. It will go up, so that'll be a plus X. And now our new equilibrium we can write with these expressions, just as we did last time. And we can think about this graphically as well. So we can have, if you just plotted out what our concentrations of all of these things were, right at equilibrium when we start, they would be flat lines because they're not changing. Right? If we added now, our disturbance is adding more Cl2, right? We add more Cl2. Now there's going to be a change. Okay, we add some of the reactant in this case, and then it will start to consume some of that. Okay, till it gets back to equilibrium. And a product here, right? Once we add a reactant, we're going to start producing more product. Again, that'll go up quickly at first and slow down and eventually flatten out when the reaction quotient goes back and reaches the equilibrium constant, i.e. when it reaches equilibrium. Okay. So let's try a conceptual problem here. So here we have a reaction where we have hydrogen sulfide plus oxygen goes to sulfur and water. Okay, and this is, as the problem states, a reaction that can improve air quality, removing hydrogen sulfide, which is a poisonous gas, removing that and converting it into things that are pretty benign, sulfur and water. Okay. Let's say this system's at equilibrium and we add O2 to the mixture. So we're adding O2. And what is happening to the concentration of water? Well, in this case, water is on the opposite side of the arrow. So if we add O2, that's going to push, back to my laser pointer, so if we add O2, that's going to push the reaction this way, and H2O, therefore, that concentration will increase. All right, so O2 will increase. Okay, what about the H2S concentration if O2 is added? Well, that's on the same side of the arrow, right? So if we add O2, right, that's gonna try to push the reaction this way. Okay, so if it's pushing it that direction, we're going to use up more H2S, so that concentration of H2S will actually go down when O2 is added. Okay. The concentration of O2 if H2S is removed. Right, so there, if we're removing H2S, okay, that's on the same side as O2, that's going to push the equilibrium in the opposite direction. They'll push the reaction this way if we're removing H2S, right, pulling it out. If we push the reaction this way, the concentration of O2 would increase. Right, and then finally, H2S concentration of sulfur is added. Right, you might be tempted to say, oh, you add sulfur, it's going to push the reaction in the opposite direction, right? Push it to the left. But remember, it's only things that affect the reaction quotient, right? So probably should have done this to start, but our reaction quotient here is products over reactants. But remember, it's only things that are not pure solids or pure liquids. That's squared. Right? So the sulfur solid does not factor in. Okay, so if we add more of that, its concentration doesn't change because it's a pure solid. Right? So it has no effect. So in this case, nothing would happen. Or we can also consider what the change in a pressure or a volume could do to a reaction at equilibrium. A lot of these reactions that we look at are in the gas phase, so changes in pressure and volume will also have an effect on the concentration. We know that by the ideal gas law. Okay, so changes in pressure affect equilibrium systems containing gaseous components. Right, and changing the concentration of a gas causes the equilibrium to shift. Just as, if you had a solution and you added more of a certain chemical compound to that system, that would change the concentration. If we're dealing with gases, pressure and volume are going to change that concentration. Right. Adding an inert gas would have no effect on the equilibrium as long as the volume doesn't change. So if you're just adding another gas but the pressure and volume are staying the same, you're not going to have any effect on the concentration. Changing the volume of a reaction vessel will also cause that shift in equilibrium, assuming that the number of moles of gas is changing. Changes in pressure or volume will have no effect on the value of K. Just like when we change the concentrations or perturb the concentrations, pressure and volume aren't affecting K, they're affecting the Q and the Q relative to K. All right, so if we look at this, here's our, in the center here, our system at equilibrium. Okay. Blue plus orange goes to green. That's our reaction. That's in equilibrium here. If you increase the pressure or lower the volume, the equilibrium is going to shift to the side that favors fewer molecules of gas. So whichever side of the equation you have that has fewer molecules of gas will be favored at a higher pressure or lower volume. And the reverse of that is if you lower the pressure, so here we have the piston at a higher position, okay, there's lower pressure there or higher volume, that equilibrium is going to favor the side that has more molecules of gas on it. So let's try to predict some of these changes using this principle. Okay, so the first question, A, we have a reaction that is calcium carbonate going to calcium oxide, those are both solids, plus CO2 gas. So we don't have any gas on the left side, we have 1 mole of gas on the right side. Okay, so how would you change the volume to increase the yield of the products? Right, so we have more moles of gas on the right side, right? So we're going to, in this case, we want to favor that side, the right side, that has more moles of gas. So we would want to lower the pressure. So if we drop the pressure, or the reverse of that would be raising the volume, that's going to favor the side that has more moles of gas, which in this case would be the right side or the product side. Okay. B, we have 3 moles of gas on the reactant side and only 1 mole of gas on the product side. So in this case, it'd be the opposite. We have less moles of gas as on the product side. So how would we favor that? How would we shift that? Well, we'd raise the pressure or decrease the volume. Right, so that increase in pressure, you can think of it's just going to force, you have less room, less volume, higher pressure, it's going to favor less moles of gas because you have less space to take up, I guess that's the way you can kind of think about it. Okay, and then finally, Cl2 plus I2 goes to ICl. And in this case, we have the same number of moles of gas on each side, that we both have 2 moles of gas or 2 molecules of gas on both sides. So in this case, changing the pressure or volume is going to have no effect. There's no difference in the amount of gas on each side, so there's going to be no driving force here for any change with respect to pressure or volume. We can also change temperature of a system. And so to determine the effect of a change in temperature on equilibrium, you have to consider heat as a component of the system. So we're going to go back to our delta H's and the sign of delta H specifically. Right? Remember when we have delta H as a negative value, that's an exothermic reaction. Okay, so you can think of exothermic, heat is being given off by the reaction. So in a sense, heat is a product of the reaction. Okay, so for exothermic reactions, heat is a product. The opposite's true for endothermic reactions. That's when delta H is a positive value. Heat is going to be a reactant. You can kind of think of it as heat. You need heat to make the reaction go, so heat is a reactant. So an increase in temperature is adding more heat to the system. So it's going to favor endothermic reaction. Right? A decrease in temperature is going to be removing heat. So that's going to favor an exothermic reaction. Right? The only factor that affects the value of equilibrium constant, or K, for a given system is temperature. Okay, so for a reaction with delta H that's positive, an endothermic reaction, increase in temperature will cause K to increase. And for a reaction with negative delta H, exothermic reaction, increase in temperature will cause K to decrease. And this is given by the Van Hoff equation, where we have comparing two different states. Okay, the ln of K2 divided by K1 is equal to minus delta H of the reaction over R times 1 over T2 minus 1 over T1. So T2 is the temperature that gives equilibrium constant 2, and T1 is the temperature that gives equilibrium constant 1. Okay. So let's try a conceptual problem here with this concept. How does an increase in temperature affect the equilibrium concentration of the underlying substance and K for each of the following? Okay, so our first reaction is calcium oxide plus H2O goes to calcium hydroxide. So how does our product calcium hydroxide concentration change by an increase in temperature? Okay, this is a delta H is negative, right? So you can think of that means we're giving off heat. It's exothermic. So you just kind of think of heat here as a product. So for increasing temperature, we're increasing heat. That's going to be pushing that reaction the opposite direction, right? So that's going to mean our product concentration now, calcium hydroxide concentration, will be going down. And what about K? Well, if we remember, for a exothermic reaction, increase in temperature is going to cause K to decrease. So this is exothermic. We're increasing Q, or we're increasing T, so K will decrease. And you can kind of think of that in terms of products and reactants, right? If our concentration of our product is going down because of this increase in temperature, you can think of that in the expression for K, that product concentration will be on the top, right? So if that goes down, K, the value of K would go down. So that's a way you can remember that. B, we have calcium carbonate solid going to calcium oxide plus CO2 gas, right? This looks very similar, similar type of reaction, but what we have here is a endothermic reaction. The delta H is positive. Okay, so our Q would be a reactant, right? And remember, if temperature is increasing, Q is increasing, our heat, okay, so that we're increasing a product, or excuse me, reactant. that's going to push it to the right. Okay. And that means CO2 concentration will increase. Right, so we're increasing a product concentration. That means the value of K will also increase. Right, and then finally, SO2 gas going to S solid plus O2 gas. This is also an endothermic reaction. So Q is going to be a reactant. Increase in temperature increases Q. Right, that's going to again push the reaction to the right. This time though we're interested in SO2, which is on the left side. So SO2 concentration will go down. Okay. K, however, this is an endothermic reaction. So K with an increase in temperature is going to increase. Okay. So the last thing to consider are catalysts, and this is where we sort of make the tie back into chapter 20 material. We talked a little bit about catalysts when we discussed delta G, and remember catalysts speed up reactions, and they do that by lowering activation energy. And because of that, right, they're not changing any of the free energy, the free energy change overall of the reaction. They're just making this barrier a little bit lower. And that makes it lower for the forward reaction, but it also makes it lower for the reverse reaction. Right. They have no, again, no effect on overall thermodynamics. They just speed things up. Okay. And because they speed things up, they allow a reaction to reach equilibrium more quickly. But they don't have any effect on the overall equilibrium position. Okay, so they're not going to change the value of K, the equilibrium constant. They would just speed things up. Right, so here, a summary table of the effects of disturbances on systems at equilibrium. You can kind of go through this, maybe studying for an exam, just to make sure that you have all of these conditions, if they all make sense to you. Right, and here's another table. It's from a different source than the book. It kind of goes through the same thing, but I thought that this was kind of a good one to go over, right? So if you look at this, let's say, you increase the concentration of a substance. What does that do? It shifts the reaction away from the substance, and then it kind of gives you a why. Why does it do this? Well, the extra concentration needs to be used up to get back to equilibrium. Right, so you can go through these and just as a summary. Okay, let's try another question, maybe a little bit more in depth here. Okay, we have the following reaction. X plus Y2 goes to XY plus Y. Right, and we're being told that delta H here is positive, so this is an endothermic reaction. And we have three different reaction scenes here to depict mixtures. So X is going to be green and Y is purple. Okay, so the first part, we're being told that the equilibrium constant is 2 at the temperature of this reaction. Which scene represents the mixture at equilibrium? So, probably better to do it on this slide. So our equilibrium, let's write out what our equilibrium expression would be. So equilibrium expression would be concentration of y times concentration of xy divided by concentration of x times concentration of y2. Okay, so for this one, right, we'd have to kind of look at all three of these situations. If you go through and you look at, let's see, x would just be green, a single green atom by itself. Y2 is going to be two purples connected. XY is a purple and a green, and then Y is just a single purple. So if you go through all of these pictures and count those up, and you could write down the equilibrium expression for these. So 1 would be, we'd have 5 times 3 over 1 times 1. So that would be 15. 3, if we looked at 3, we'd have 3 times 1 divided by 3 times 3, which would be 1/3. And 2 is 4 times 2 divided by 2 times 2, which is going to equal 2. Right? So we're told that K is 2 at equilibrium. So which of the scenes represents the equilibrium conditions? Well, K is 2 in scene 2, so that would be at equilibrium. Okay, part B, will the reaction mixtures in the other two scenes proceed towards the reactant or towards the products to reach equilibrium? Well, we have in case 1, Q is 15, right? We calculated that using that our expression here, right? Which is, again, the same expression you use for Q. K is at equilibrium, Q is at any other time. So if it doesn't equal 2, right, it's not K, it's Q. So Q here is bigger than K. So what does that mean? That means we have more products than are necessary. So the reaction would shift to the left to reach equilibrium. Okay, and the opposite for scene 3, Q is 1/3, which is smaller than 2, smaller than K. So this, we don't have enough products, so this would shift to the right until it reaches equilibrium. Okay, and then finally, for the mixture at equilibrium, how will a rise in temperature affect the concentration of Y2? So remember, Y2 here is a reactant. This is an endothermic reaction. So what does that mean? That means Q is a reactant. Okay, and if we're increasing, raising the temperature, right, we're adding more Q, we're adding more of a reactant, so that's going to shift this equilibrium to the right, so we would actually use up more Y, so that concentration of Y2 would decrease. Okay. So that was a kind of a conceptual question using the principles we've talked about. Right, the book talks about this reaction, the Haber process, and this is the synthesis of ammonia. And it was developed by this guy, Fritz Haber. And it is actually a very, might not seem like it just by looking at it, but it's really important. It's important in the development of synthetic fertilizers, which actually, you know, help produce more food, and at the time was seen as a very very important use of chemistry. and I believe he won the Nobel Prize for this, which was a little bit controversial in the fact that he was also responsible for developing chemical weapons that were used by Germany in the First World War. So he kind of had two sides there to him. But anyways, this reaction, we have N2 gas plus H2 gas goes to NH3 ammonia, and it's an exothermic reaction. Right? There are three ways to maximize the yield of NH3, right? You can decrease the NH3, the concentration of this, right? So how do you do that? So you would remove it as soon as it's formed. Okay? And so this reaction, I'm sure this reaction was known before Fritz Haber developed it. But what he did was he thought, okay, how can I use Le Chatelier's principle and equilibrium to maximize the production of the ammonia? Okay, and you can do that by removing NH3. You can decrease the volume or increase the pressure, right? And that's going, if you look at the number of moles of gas on both sides, we have 1 plus 3 reactants, so 4 goes to 2 moles. So we're decreasing the number of moles of gas from left to right. So if you increase the pressure or reduce the volume, that's also going to shift that reaction to the right. And then finally, because it's an exothermic process, Q would be a product. So decreasing the temperature would be the same as kind of like removing a product, and it would shift the reaction to the right. Okay, so if you do all three of these things to it, you're going to produce more of your product, ammonia. And if we look at, so this is a industrial real-world application for Le Chatelier's principle. So if we just looked at some of this data here, you have at increasing temperatures, the equilibrium constant here, you can see it goes down, okay? And remember, this is an exothermic process, so increasing the temperature is like increasing a product, and it's going to shift the equilibrium to the left, right? So you want to lower that temperature. You want to keep it as low as possible to get that equilibrium constant as high as it can be. Right, so if we made a plot of this temperature versus your yield of NH3, and then this might be a little bit hard to read because each of these lines represents a different pressure, okay? So remember, we also wanted to increase the pressure to increase the yield. So there's definitely a trade-off between temperature and pressure. So this is kind of like real-world situations. If you just considered this, right, you'd go, okay, yeah, we want to keep that temperature as low as we can to make K as big as possible. The problem is when you do that, the kinetics of it might slow down to such an extent that the reaction just becomes very, very slow. The equilibrium position might lie towards the products, but the time it takes to get there might be pretty slow. So there is a trade-off. So in the industrial conditions shown here, you don't get 100% yield necessarily, but you get, it's a good trade-off between the yield of NH3 you get and just how easy it is to create certain pressure and temperature conditions. And if we looked at that in terms of a block diagram, this is something you might see, like for engineering processes. When I was going through chemical engineering as an undergrad, we looked at a lot of these types of diagrams. Right? So if you have your two reactants, you put them into a compressor, okay, that raises the pressure. they flow over a catalyst, so that catalyst there, it's trying to catalyze this reaction as well. So you're producing your NH3 when you're doing that. You go into another stage that actually condenses the ammonia and removes it. Okay, so then you're putting back everything else that isn't your product, ammonia, back into the compressor. Okay, so you're in this. If we look at this, what are we doing? What principles are we using? Well, we're using a higher pressure, right, to drive that reaction to the right. We're using a catalyst to speed that up, and we're removing a product to, again, drive the reaction to the right. Okay. We can also think about, biological systems. So here we have isoleucine synthesized by threonine. Okay. You have different enzymes in this step. Obviously, this isn't something you have to know for this class. What I wanted to bring up and why the book shows it is that you also have this case where a product, the end product of your series of reactions, will actually feed back and inhibit the enzyme, typically the first enzyme in this step, so that, if you have enough of this as your product is formed, it kind of feeds back and stops this process, this chain of reactions, right? Because if you have enough isoleucine, you don't have to waste any more threonine synthesizing it. So this is an example of feedback inhibition. Okay, not super important for this class, but if you go on to biochemistry, you'll see this again. Okay. And the inhibition, just for your information, typically what happens for inhibitors is that you have an active site in an enzyme. So this structure here is our enzyme. The active site is where our molecule goes in that gets, in this case it would be a threonine, goes in there, gets converted to isoleucine by this enzyme. Our inhibitor now binds to a different site on that enzyme, and it will change the active site shape so your threonine now can no longer go in. Okay. So if we, going back now to chapter 20, section 4, right, if we're considering delta G with respect to equilibrium and the direction of the reaction, right, we know that if Q is less than K, if we did that ratio of the two, Q over K, it would be less than 1. Okay. So if we took the log of Q over K, that would also be, it would be negative. Okay. Delta G is going to be negative in that situation. Okay, so that's a case. Well, what does delta G mean? Well, remember delta G means the reaction's spontaneous. So that's a case where the reaction is going to spontaneously go to the right. The opposite of this would be when Q is bigger than K, that ratio will be a larger than 1. So the natural log of that would be a positive value. And likewise, when delta G is positive, that's a case when the reaction would proceed to the left. Okay, so when Q is smaller than K, the reaction moves to the right. And when delta G is negative, the reaction moves to the right. When Q is bigger than K, the reaction moves left, backwards. And when delta G is positive, the reaction would move backwards. So these are related. And that's where we get this ln of Q over K, whether it's negative or positive, from. Right. At equilibrium, Q equals K, right? That ratio is 1. The ln of that would be 0, and delta G is 0. So delta G at equilibrium is 0. Right. They're all related by this equation. So delta G equals RT times the ln of Q over K. You can also express that if you wanted to break this up, this ratio, you express it as RT times ln of Q minus RT times ln of K. Right, so if you're doing the algebra on this, right, this is how you address that. Okay. If Q and K are very different, delta G is going to have a large value, right, either positive or negative depending on which one is bigger. And that means that the reaction releases or absorbs a large amount of energy. Okay, if Q and K are close to the same or about the same, delta G, that value is going to be very small. Right, so for standard state conditions, Q is 1. And remember, why is that? Well, at standard conditions, the concentrations of everything is 1. Okay, and the partial pressures of gases is 1 atmosphere. So that means if you were trying to do calculate Q would just always be 1 at standard conditions. So we can write a delta G value at standard conditions, and we call that delta G naught, and that equals minus RT ln of K. All right, if we just backed up here, if we plug our value of 1 in for Q here at standard state, this whole term would be 0 because the ln of 1 is 0. So that would drop out, and we're left with minus RT ln of K at standard conditions. Okay, a small change in the delta G naught causes a large change in K due to the logarithmic relationship. As delta G naught becomes more positive, K is going to get smaller. And conversely, if delta G naught becomes more negative, K becomes larger. And you can think of that too. The more positive your delta G naught is, the more that reaction, I should say, the less spontaneous it is, right? The harder that reaction is to go forward. And how would that look like in terms of equilibrium? It would mean the reactants are being favored, so the equilibrium constant, right, the reactants are in the bottom of that expression, so it would become smaller. So these are sort of inversely proportional. To calculate the delta G for any conditions, how would you do that? Well, you would use this equation. Delta G equals your delta G naught plus RT times ln of Q. So whatever your conditions are, right, you would have your delta G naught, which takes into account your equilibrium position, your equilibrium constant, okay? And then, whatever conditions you're at the moment, the varying concentrations you have, this term here would factor in. Okay, so let's use this and try some practice problems. Okay, so we have NO plus 1/2 O2 gas goes to NO2. All right, the first part, use Appendix B to find K at 298 Kelvin for the following reaction. So let's, switch to the pen. So part A. So if we look these values up, we would need a delta G naught and we have our reaction. Let's remember our reaction. Oops. And mess that up. NO gas. Okay. So that's a 1. This is a 1, and 1/2 for oxygen. Okay, so if we're looking these values up in the back of the book, our products is just NO2. So we have 1 mole of it times 51 kilojoules per mole minus the sum of our reactants. So 1 times 86.6 for NO plus 1/2 times 0 for O2. So we get negative 36 kilojoules. So that's our delta G naught. R, right, that's just always going to be 8.314 joules per mole Kelvin. And so our equation is delta G naught equals minus RT ln of K. Right, we can rearrange this to be solve for ln of K. That would just be delta G naught divided by minus RT. So delta G naught is minus 36 kilojoules, but that would be 36,000 joules, divided by minus R, which is 8.314 joules per mole Kelvin, times our temperature, which is 298. So then we get ln of K is 14.53. And to get rid of that, right, we would have to do e to the 14.53 power. Which is something like 2 million, 2 times 10 to the 6. Right, so that's a very large value. Okay, part B, use the equilibrium constant to calculate delta G naught at 298 for the following reaction. So here we have another reaction, 2HCl plus H2 plus Cl2, and we have a given K value and a given temperature. Right, so in the first part, we look up a delta G value and we use that to calculate a K. Now we're given a K value and we use that to calculate our delta G naught. Delta G naught, again, is equal to minus RT ln of K. And we're given everything, so we can just plug it in. So 8.314 joules per mole Kelvin times 298 Kelvin times the natural log of 3.89 times 10 to the minus 34. So that's a very, very small equilibrium constant. And therefore delta G naught is going to be a positive value. That would be 191 kilojoules. Okay. So in that case, if you're given a equilibrium constant, it's very easy to calculate a delta G naught. Right, so the relationship again between delta G naught and K, when delta G, I should kind of say when K is very small, delta G naught's going to be very positive. When K is very large, delta G naught's going to be very negative, which means the reaction would go towards the forward reaction, right, the right side. And when delta G naught is a very positive number or K is very small, that's essentially a case where you don't have any forward reaction. Everything goes to the left, or the reverse reaction. Okay, so let's try another one of these problems. Okay, we have 3 molecular scenes. We have A2, which is black, B2, which would be green, and then they form AB, which would be a mixture of the two. And that's given by this reaction. Each molecule represents 0.1 atmospheres, so they have the same partial pressures. The delta G naught value here is negative 3.4 kilojoules per mole. First part, A, if mixture 1 is at equilibrium, calculate K. Okay, so we have our expression for K here is going to be AB, concentration of AB squared, or pressure of AB squared, divided by A2 times B2. Right, so if we add all those up, if we look there, what do those? Yes, so here, right, you could use, technically you could use the partial pressures, because they're saying each molecule represents 0.1 atmospheres. Or you could just count up the number of molecules. You'd get the same thing. But since they're giving us the partial pressures per molecule, let's just do that. So the pressure here for AB, there's 4 of them, so it'd be 0.4. There's 2 of each of the A2 and B2, so those would be 0.2 and 0.2. Okay, so our K value is going to be 4. Okay, so part B, which mixture has the most negative delta G? And which has the most positive? Well, to do that, we would need to actually calculate those delta G's, right? So how do we do that? I'm going to move it to this slide, give more room. Okay. So for B, right, we know delta G naught equals minus RT times ln of K. All right, so we know K, we calculated K from the first part. What we don't know here is a temperature. So if we go back, right, we're given our delta G naught, we're given we're found K in the first part, right? And to get a delta G that is a delta G at any conditions, right, not just standard state, we need to know delta G naught, we need to know K, and we need to know temperature. Right, but that's the one thing we're not given is a temperature. Okay, so we need to rearrange this equation to solve for temperature. So if you do that, you get temperature equals delta G naught divided by minus R times the ln of K. And we can plug everything in here. So our delta G naught is 3.4 kilojoules per mole. We're going to need to convert that to joules though, so we would multiply that by 1,000. Okay, divide this by minus R's 8.314 joules per mole Kelvin, and ln of K, remember we calculated that as 4 in part A. When you do this, we get 295 Kelvin is our temperature. Okay, so then we can go back to each scene and count up, all the products and reactants and calculate a value for Q for each of these. So in the case of scene 1, right, this is at equilibrium. Delta G is 0 because it's at equilibrium. So delta G equals delta G naught plus RT times ln of Q. Right, so if you plug all those values in, you're going to see that you have negative 3,400 joules per mole plus positive 3,400 joules per mole. That would equal 0, right? Which it should be at equilibrium. So for scene 2, this is more important, right? If you actually calculate the Q for this, that would just be the concentration of products over reactants. The Q is going to be 0.44. Right, so again, we would plug this value of Q in to our equation for delta G. So we have delta G naught, which is minus 3,400, plus RT ln of Q. Right, so that's minus 3,400. I'm going to not include the units just because to save some space. But you can see them up top there, they cancel. So 8.314 times 295 times the ln of 0.44. So this value equals minus 5.4 times 10 to the minus 3 joules. And then finally, scene 3, Q equals 36. Right, so if we, whoops, where'd my pen go? So if we plug that in, same equation, okay, minus 3,400 plus 8.314 times 295 times the ln of 36. What would we get? We would get 8,800 joules. Okay, so the question's asking which one of these is the most negative. Well, scene 1 is at equilibrium, it's 0. Scene 2, Q is very large compared to K. K is 4, Q is 36. Q is bigger than K, which means you have too many products, which means the reaction would go backwards. That means it's not spontaneous the way it's written, so delta G is going to be a positive value. Okay. So the one that's most negative is condition 2. Okay, it is, we have a case where Q is less than K. Q less than K means you need more products to get to equilibrium, and that means it's a spontaneous reaction the way it's written, and delta G is going to be a negative value. And then finally, remind ourselves what the question was. Is the reaction spontaneous at the standard state? That is, everything has a partial pressure of one atmosphere. Right, so how would we solve this? Well, we would need to calculate a Q for that condition, right? So if everything is at, we could use the partial pressures now. So if everything's at 1 atmosphere, right, we'd have 1 squared for our products divided by 1 times 1 for our reactants, right? That's just going to equal 1. Okay, what is K? K is 4. So in this case, Q is less than K. Right? So when Q is less than K, what does that mean? That means your equilibrium lies in that direction to the right. So yes, this would be spontaneous. And when you do the math on this, delta G would equal delta G naught at standard state. Sorry, I almost sneezed there. Delta G would equal delta G naught. So if you just did the math real quick, right, delta G equals delta G naught plus RT times the ln of Q, right? If we plug Q, if Q is 1, the ln of 1 equals 0, right? So this whole term would cancel out, and you're left with delta G equals delta G naught. And we can see delta G naught here is a negative value. So yes, it's spontaneous. 2 ways of thinking about that one. Okay, last question. Oxidation of SO2 is too slow at 298 Kelvin to be useful in the manufacture of sulfuric acid, so the reaction is run at high temperature. So our reaction is 2SO2 plus O2 goes to 2SO3. Okay, so first calculate K at 298 and at 973 Kelvin, and we're given a delta G naught value at 298 and a delta G naught value at 973. Okay. Second part, 2 containers are filled with half an atmosphere of SO2 and 0.01 atmospheres of O2 and 0.1 atmosphere of SO3. One is kept at 25 and the other at 700. In which direction, if any, will the reaction proceed to reach equilibrium at each temperature? And then finally calculate delta G for the system in part B at each temperature. So let's try part 1. Or part A, I should say. Okay, we know our reaction, again, is 2SO2 plus O2 goes to 2SO3. So we have delta G naught equals minus RT ln of K. So we can rearrange this to solve for K. K equals E to the minus delta G naught over RT. Okay, so that's, this equation solved for K. So you might be good to kind of remember that one too. You can use, if you're given a K value, you can use it to solve for a delta G. If you're given a delta G, you can use that to solve for a K. So at 298, what do we have? Well, let's just look at this exponent term, delta G naught over RT, the negative value of that. Right, and we're given in the previous page, we're given a delta G naught of minus 141.6 kilojoules, which would be 141.6 times 10 to the 3 joules per mole. Okay, divide that by 8.314 joules per mole Kelvin times 298. So that would be 57.2. So our K would be E to the 57.2, sorry. That's a K equals E to the 57.2 power, which would be, you know, something really, really large, 7 times 10 to the 24th. So very large K at that temperature. Okay, at 973 Kelvin, right? We'd plug everything into that same equation. We get a delta G value now at 973 it's not quite so large. It was negative 12.12. Again, I'm going to skip putting units in because we've shown them above. We're just doing the same thing, so we know they cancel. So that term becomes 1.5. So K equals E to the 1.5, which is 4.5. And does that make sense? Well, yeah, if you have a delta G naught value that is a much bigger negative number, that means it's very spontaneous. It's going to favor the products, and that's what K shows. We're getting a much bigger value for K for that situation. Okay, so let's move on to part B. Okay, so for part B, we're given a bunch of pressures or partial pressures. So that's kind of a hint. We need to calculate our reaction quotient in terms of pressure. So we have products, SO3 over reactants, and this would be the pressure of SO3. Pressure of SO2 squared and times the pressure of O2. And those were 0.1 atmospheres, excuse me, 0.1 squared. No, not squared. You know what? Let's just erase that. Point 1 over 0.5 squared times 0.01. And that comes out to be 4. Okay, so our K value we calculated previously, right? So in here we have a Q of 4. That's going to be less than K at that situation. And when that happens, that means your products are lower than they should be, in a sense. So the reaction goes to the right, favors products. Okay, finally, part C. Okay, part C, let's remind ourselves what the question is. Calculate delta G for the system in part B at each temperature. Okay, so delta G equals 298, and delta G at 973. So remember, we have delta G naught plus RT ln of K, ln of Q. So we can just plug all of these values in. So minus 141.6 kilojoules per mole times, plus 8.314 times 298 times the ln of 4, right? That was the Q that we calculated in part B. So under those conditions, our delta G is negative 138.2 kilojoules per mole. And at 973, right, again, we have our delta G naught, which we've found, times our plus RT times ln of Q. Right, so this one is 12.12 kilojoules per mole plus sorry, I didn't show this. So here, right, we needed to convert R into kilojoules, so it'd be times 10 to the minus 3. Sorry about that. Let's do the same thing here, 8.314 times 10 to the minus 3 times 973 now, that's our new temperature, and times ln of Q, which again is 4. We get negative 0.9 kilojoules. So you can see in this case, right, it's a very small negative, but it is negative, so it becomes spontaneous. Right, the figure 20-15 is kind of a good summary of this. It shows the relationship between negative delta G's and positive delta G's with respect to Q and K. So I think this is a very good figure to kind of look at as a summary for this part of for this section of the book. Okay, so that concludes chapter 17 and the last of chapter 20 that we're going to talk about. The next section we will be moving on, but this kind of ends what we're going to be covering on the first exam. So just to review, chapter 6, chapter 20, and chapter 17 will all be on exam 1. This will be an hour and 50 minutes. It shouldn't really take that long, but you'll have the whole time if you need it. It's closed book and closed notes, and do remember to bring a calculator. You'll obviously need that. We've been doing a lot of math. Okay, and good luck on the exam, and hope you all do well.